All right, welcome back. Um, in the last example, we looked at three vectors in R3 and figured out that for them to be linearly independent, this matrix had to reduce to In to make sure that you had a unique solution here. A1 is 0, A2 is 0, A2 is 0, and A3 is 0. All right, and so it meant that the matrix was invertible, or even better, the determinant of A is not 0. And that was easy to test because the determinant is easy to compute even with X. All right, so let's look at this takeaway that recaps what we've learned there. So a subset of En, if it's equal to V1 for Vk, it is linearly independent if and only if I put them in a matrix, like so, and I reduce it, I'll get one leading one for each column. All right, so I need a unique solution. That means I need no free variable, and so a leading one in each column. Now, if I have the same number of vectors as the dimension, then I get a square matrix, and then it's more interesting. It's going to be linearly independent if and only if this matrix A, let me give it a name, this matrix A is invertible, or we could say it's linearly independent if and only if the determinant of A is not 0. All right, so that's very helpful computationally. All right, now let's try examples that are not in Rn that live in more general vector spaces. So let's try one with matrices here, and then in the next video we'll try one with functions. All right, so I want to know whether the subset of these three matrices is linearly independent or dependent, and I'm going to use theorem 1.4.1, the one about number of solutions. If possible, give a dependence relation for S. All right, so I want to know how many solutions I want 0, so the 0 matrix here is equal to A1 times the first matrix, so 1, 2, 1, 1, plus A2 times the second, plus A3 times the third. And so let me squeeze that a bit. It's a bit too big. Sorry. All right, almost there. All right, and so if I put them all in a matrix, what I'll get is A1 plus 3, A2 minus A3. I'm going to get A1 plus 2, A3. I'm going to get 2A1 plus A2 plus 3, A3. And I'm going to get A1 plus 5, A2 minus 3, A3. Right, so I want to know when that's 0, that's going to give me a linear system. And if I put it in the matrix, the first equation is 1, 3 minus 1 equals 0. Second is 2, 1, 3 equals 0. 1, 0, 2 equals 0. And 1, 5 minus 3 equal 0 as well. All right, so let's reduce it. I got 1, 0, 0, 1, 0, 0, 0, 0. So far so good, but the third column gives me no leading one, so I do have a free variable. So that means infinitely many solutions. and so it's going to be linearly independent. In fact, if I were to write the solutions, I'm going to get A1 is minus 2s, A2 is s, A3 is s, where s is this free variable here. And if I take at s equals 1, I'm going to get A1 equals minus 2, E2 equals 1, A3 equals 1. That's a non-zero solution. And so we have linearly dependent. All right, so as soon as you know infinitely many solutions, you know it's linearly dependent. But because I had this extra sentence here, because I was asked if possible to give a dependence relation, I knew I needed to get one specific solution here. So minus 2, 1, 1 would work. And so I know that minus 2 times the first matrix plus 1 times the second plus 1 times the third is equal to 0. All right, always the 0 of your vector space, and so this is my dependence relation. All right, in the next video, we'll do one with functions, which is more complicated because in functions, you have tons and tons of different functions. It's not like matrices that it's more or less or for. Functions are way more complicated.